All right, so I feel like I want to go back through chromatography, gas chromatography, and talk about what it is a little bit more because last night I was kind of in a rush. I wanted to get the lab started, so this might help. So up here you have a little picture of what is actually going on. So when we adjusted the pressure from 7 kPa to 6 kPa, what we were adjusting is the pressure of this gas that's being pushed through the column right here in order to get your sample through, right? So there's gas that's being pushed through this column, and that helps, that serves as sort of like a medium for your sample to flow through the column. All right, so you inject your sample, which is a liquid. That liquid goes into a heated column, so that this is heated. In the column is what we call a stationary phase. I think the word phase is sort of awkward here. I feel like a medium would be a better way to describe it, but basically it's a coating that's on the inside of the column that your mobile phase or your sample is going to either stick to or not stick to. Okay, so it's basically like you're moving down a moving like walkway at the airport, and you either keep getting off and back on, or you just go straight through. And depending on how attracted your mobile phase is to the stationary phase will determine how fast this goes through. So if your mobile phase is attracted to the stationary phase, and in our case stays a liquid for longer, the liquid is going to be more attracted to the stationary phase. So it goes through the column really slow, and it will take a longer time to come off. If your mobile phase starts as a liquid and as the temperature ramps up, turns gaseous pretty quickly because it has a low boiling point, it's going to fly through the column much faster and hit the detector first. So that's in the column's long enough that it allows for your particles to go through and separate enough so that we get our chromatogram will have 2 or 3 or 4 separate peaks depending on how much stuff is there, and we'll be able to identify them based on how long they sat on the column. Remember, we're going to run all 4 of our materials separately so that we can then identify on our final sample where all 4 of them are, we can identify which is which. So anyways, you have this stationary phase on the column that is attracting your mobile phase. Your mobile phase will turn gaseous depending on its boiling point. So lower boiling point will turn into a gaseous state sooner and therefore will move through the rest of the column faster than one that doesn't. So last night we put in methanol and propyl acetate. All right, so they start going through the column together. So you inject them, you inject them, and we have, let's see if I can do this. Oh, there we go. They move through the column. All right, so then what happens is, although they start moving, your little ones and your methanol, because they are now less attracted to the stationary phase, will start moving faster. So now, although, that's not what I want to do. Although they are both moving through, again, not what I want to do. Let's see if I can get there we go. Your blue guys, your methanol, are going to travel at a rate that is faster than your red guys or your propyl acetate because of the boiling points and the fact that your methanol turns into its gaseous state sooner on the column than your propyl acetate. So they move, 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 move. All right, so then your detector is like the finish line. So your methanol moves, 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 and it hits the detector, boom, and there's the finish line for the methanol. So the methanol all comes off. And you see as it passes the detector, you'll see that spike in the gas that's coming off. All right. And then a couple minutes later, your slow poke propyl acetate, which is moving at a snail's pace, will then cross the detector and we'll get another peak later on. And your retention time, again, is just time spent on the column, and it's shorter for things with lower boiling points and longer for things with higher boiling points. What we're going to do, and what we did do, was we mixed these two together, added acid. So over the week, these two are going to react and form methyl acetate and propanol. However, it's not a reaction that's going to go to completion. So we're not going to completely get rid of methanol and propyl acetate. We're expecting their concentrations to go down, but we're not expecting them to disappear. So far, we've been talking about reactions that go to completion, so your reactants completely go to zero and your products grow in to the highest amount that they can. But in this case, remember we talked about, a little bit about that treadmill. So these guys are smacking together and forming products at the same rate that these guys are hitting each other again and forming reactants. It's called an equilibrium. So what we will see next week is a certain amount of each. We'll have a peak for each of these reactants and each of the products. So instead of just having the 2 peaks like we saw last night, we'll have 4, and we'll have to identify them and figure out their concentration by doing a little math with our numbers for the integration. And we will figure out how these are balanced out. So basically it's called K. We'll talk about it next week, but we're going to figure out the equilibrium constant for this reaction. So are we favoring, it will tell us if we're favoring products or if we're favoring reactants. But either way, that's what's going on. So next week we will work on getting individual spectra for each of these, individual chromatograms for each of these, and then one final of your mixture at completion. And then I'll show you how to do the math. So I hope that helps. If you still don't get it, Google it. There's a bunch of videos. I saw some. They were just kind of boring, and I'm much more fun, so figured I'd make my own. But anyways, have a good weekend, and I will see you next week.